Welcome to presentation 33. In today's presentation, I'm going to be talking about the NRF24L01 transceiver. Now the transceiver belongs to our layer 3 architecture, wireless transceiver, and we're going to use the UART framework, SPI framework, IO port framework, and an interrupt external framework in our development, those from the layer 2. So let's look at the agenda. So what I'm going to be doing today is, first I'm going to give you descriptions of the transceiver. Next we go to schematics to show how to hook it up. We'll follow by looking at the NRF24L01 data sheet. Next, we'll create the framework based on that data sheet. Next, we'll look at the different parameters and how to configure the radios for the receiver and transmitter. Then we'll go through sample program 1 and 2, which are the receiver, one using the polling method, the other using the interrupts. And finally, we look at the sample program 3, which is going to transmit the data. So the NRF24L01 is a low-cost wireless communication chip made by Nordic Semiconductor. It lets two or more devices talk to each other using radio waves. It's on the 2.4 gigabits band. Now this is a radio that runs in the $3 to $4, so it's very reasonable price. So that opens a lot of doors for you to do things. Let's look at the main features. So can send and receive data up to 100 meters in open space. It's low power, which makes it great for battery powered projects. Can transfer. You have three choices: 250 kilobytes, 1 megabyte, or 2 megabytes. In the sample program, we're going to be using the 1 megabyte because that's usually the one that we've been having more success in the transmission, because as you increase the megabytes, you start losing too many transmission parameters. Now, two-way communication, so means that we can both send and receive messages, which means the device can talk back and forth. I should say that with the 1 megabytes and with 2 megabytes, we lose more messages. That's what I should have said. Next, it supports 6 devices, so you can have 6 different addresses. Talk to 6 devices, taking one receiver at a time, of course. And the devices, each connection to each device is called a pipe. So when we get into configuration, I'm going to be talking, hey, I'm going to configure pipe 0, for example. So I can configure pipe between pipe 0 and pipe 5. Next, it has an auto acknowledge. Receiver can confirm it got the message. So the auto acknowledge, we can configure it, but we can also configure for no acknowledgement. So we have those choices. So now when we talk to the radio, I should say the controller, we're going to be using the SPI protocol. So now let's look at the data sheet. No, I'm sorry. Before we look at the data sheet, let's take a picture, see what the actual radio looks like. So we have this is the radio. It has 6 pins for communication. And these are the values. We have the ground, chip enable, clock, MISO, IRQ, MOSI, and chip, and this is the chip select, and this is the chip enable. So when you want to communicate, you have to set this chip enable. When you want to communicate through the radio, you want to transmit something or you want to receive something, EE. When you want the microcontroller and the microcontroller and the radio to communicate, then you do the chip select, which is called the CSN. And then we have the voltage. You have to understand that that's a 3 volt, so you're going to need something to go between your 5 volt of your controller and the radio. So here we have the interface I'm going to be using. So we have the clock, MOSI, IRQ, chip enable. Chip enable is this one, and this is radio enable, so we can communicate. So those will be going into our controller via, and we have the 4050 in between. So this is going to handle the between 3 and 5 volts. So we have the clock, the MOSI, the interrupt 0, which we're going to hook up our IRQ. We have the chip enable and chip select. Now the MISO is going to be hooked up directly because this is a one direction. The MISO sends data to the controller, and anything that the controller replies or sends back is going to go to the MOSI through this chip. It's important that you do it this way, or things are not going to work. So let's see if there is anything else we need to understand here. So anyhow, that's how we connect, and this is another picture of the controller. So now let's go and look at the data sheet. This is the Nordic Semiconductor NRF24L01 transceiver. Now, as usual, my goal here is to give you the highlights of the document so then you can go back and review it yourself. So let's get going. So the first thing I wanted to show you is the page where they have the features. This is a good place to start because it's going to give you some of the capabilities of the radio. So you have in one location the different capabilities of the radio, and the important thing about this is that as you go through this list, you have to get in back of your mind that those are things that you are going to have to configure. Next, we have here the state diagram. The state diagram is something that you're going to have to look at it, and that's going to give you a good idea of how things are going to have to flow. And so you have to kind of give it a good idea. You have, in general, you go from power on, then you go to standby, then you're going to transmit, or you're going to receive, and then you go back to standby, and then you can go to power down if needed. So let's go to some of the information we have here. So we have a little bit information about the power down, standby modes, the receive mode, transmit mode, and then here they show you a table which is somewhat important because it tells you, hey, if you want to be in the receive mode, then of course the power up register has to be 1. Then you have something called the prim underscore RX register has to be 1, and the chip enable has to be 1. So then it gives you the different configurations if you want to get into transmit mode. And so there's a lot of information that you're going to have to actually use when programming. But anyhow, I'll show you during the programming, but you know where I got it from. So let's go next to
So here I'm just going to touch on some of the items that you are going to have to program. So for example, the RF channel frequency, this gives you the different frequencies that you can set up. Next, you have the PA control. What is this going to, when you're going to set up this so to manage the output power of the radio. So it's going to depend whether you're really close or really far uh, of I should say the distance between the transmitter and receiver. The farther away you are, you're going to have to change these values to make sure the signal goes that far. Next, you have the receive and transmit controls that you're going to have to configure, of course. And then finally, what you have here is the enhanced shock burst, which is what the NRF24L01 proprietary uses for the transmission. Next, we get into the data and control interface. Basically, this is where the messages that we can send to the from the controller to the radio to command it to do something or to configure. So we have the IRQ, chip enable, chip select, clock, MOSI, and MI. So those are basically our SPI signals plus the chip enable, which is something to enable the radio to transmit. So as I noted, we have commands. So we have a table here with the commands and that we're going to have to send through the SPI interface. So I'm going to prepare a framework, which I'll show you next, to be able to manage all these commands. So every time you have commands and you have configuration stuff, immediately in back of your mind you need to think about frameworks to manage this thing. So these are the different commands that you can send the radio. And next, we have the register that we have to manipulate to configure the radio. So we send command to the radio things to do, and then we have to configure register to say how is it going to do it. But so first you have to, of course, you need to configure the register. But actually, to configure the register, you send a command that says, "Hey, I'm configuring things." So they are hand by hand, which to say. So here you have all the different addresses that you can access to do configuration. And finally, I'll just go to application example. This shows you how the chip is hooked up to your system for the radio. So you could have whatever system you have, and you can take this NRF and incorporate it into your design. So what I did is a quick review of a whole document with at least with 74 pages in a couple of minutes, and that gives you an idea that you have to come back and you have to look at where you can find things, I should say. So let's continue with the presentation.
Okay, so we know now that what the specification looks like, and that's where we have to get all our information. So now, based on that specification, I created a framework to be able to put my arms around all this data. So let me show you. So we have the information that we are going to get from the specifications. We have commands, and we have register that we can modify to configure the system or tell the system to do something. the commands are on the flavor of the commands are read, write, flash, acknowledge or not acknowledge. So that's the value. That's what we get with the commands. And what I did is from the spec, I got the numeric command description, and based on that, I started creating my framework so I can do something with this. If I want to, for example, the write to the register, so I'm going to have to send this information, and then I'm going to have to order it with something to see what register, what memory map, the address of the memory map. So that would be these 5x's. So I'll go through some of that stuff later on. But first, I'm just going to go straight through the framework, and you can just see where I got the data from. So here we continue with each of the tables on the spec. So there is the only thing that I'm creating here is adding the code for each of the lines. And what this ensures is that I've accounted for all the commands and the registers. So at the end of the day, I end up with my framework. So sometimes you look at somebody's code and you say, wow, look at all this stuff. Where did they get it from? Well, this comes directly from the document, and all you have to do is account for all your commands and your register addresses. So let's look at some of this stuff a little bit closer. So let's look at the ones associated with write. Either we can write the payload, which is something that we're going to transmit, or we can write into a register, which is something that we're going to configure. So let's start by looking at writing to a register. So we write to a register, we need two pieces of information to send to this routine. One is the register we want to write to, and then the value. So of course, first we select the radio, then we send the command, which is going to be the W register, which is 0x20, and that's this value here, and then we have to order it with the registered name. Now, to ensure that we're only ordering it with the 5 most significant bits of the register, we end the register that comes in with the 1F, which is basically getting rid of the 3 most significant bits. We order that, and then we're going to get this complete command, which is going to write this line here, going to write to this register. And after we send that, then we send the value we want to write to it. And then we, of course, deselect the radio. Now let's look at the write to a payload. So to write to a payload, we're going to send this command. So I should back up. So when we write to the payload, we want to write the payload, we have 3 options. The first one is we're going to write to the payload and fill up the information. Next, we are going to write to the payload, but when we write it, we're going to also send the acknowledgement and the pipe where we expect to get the acknowledgement. And finally, we're going to send one which it says we're going to send the payload, but we don't want acknowledgement. So no acknowledgement. So this I misspoke here. So the first one is we send the data with acknowledgement. We send the data and we include the acknowledgement. And finally, we send with no acknowledgement. So we can send the TX payload, ACK payload, or payload no ACK. So this is what it's going to look like. So we send the register. So the register is going to be one of these three parameters. Like I said, acknowledgement, acknowledgement, plus pipe, and the no auto acknowledgement. So that's going to be the reg. Then we send the buffer, which is the data that we want to transmit. So this is the reg. Then we send the data we want to transmit and the length of the data. So we can see for I equal to 0 to the length of the data, we do the buffer sub I and we transmit. So that's the write that. So we write to a buffer, or we're going to send the payload out, and we send the payload. We have these three flavors, and this is how we send the write to the register, and this is how we send the transmit, right? The buffer that's going to eventually be transmitted. So now let's look at the read. So again, we're going to read to a payload. We're going to read from a payload that we just received, or we're going to read a register. Now, to read the register, we have to send the 000. It has to be ORT with the register we want to read from. So, so this is how we do that. So we get the register, then we ORT with the register value, and then we send, after we send that command, and then to get the data, what we do is we send another SPI transfer with the NOAP. Now this is the value of this is just 0x111111FF, and then we deselect the radio. So we select the radio, we send the register with ORT with our register value, and then we send the dummy to get the data. Now let's look at the payload. So we can read a payload by sending this message, and we are going to get a payload up to 32 bytes, which is this the number of the payload, by the way, it's hex 61. Now this is the routine that we use to read the payload. So we enable the radio, then we send the command, hey, I want to read the payload that we received, and then we send the dummy SPI with the knob to get the value. Then we deselect the radio. Now, every time we do a read and get the payload, then we need to make sure that we reset all the interrupts, so we can check when we get the next payload. Now let's look at how are we going to do the flash TX and flash RX. So now I suppose you're trying to get the flavor of why setting up the this framework helps so much. Now, if we want to flash the receive, then what we do, that means clear it basically. So we select the radio, we send just the flash command, and we're done. Then we deselect the radio. For the transmit, is going to be the same scene, except that we would meet the flash transmit. So now let's look at the timeline. How we're going to, what needs to take place for the communication to be successful. So we have both are going to do the transmit. I have a transmitter here and the receiver, and we're going to look at the differences and how they get set up. So the power up, both have to set up the power up, both have to configure register. One is going to be configured for transmission, the other one for receiving, and we'll look at that. Then we need to flash the receiver transmitter, clear IRQ, so far the same. Now, this is where we are different. The transmitter is going to load the payload, while the receiver is going to get into the listening mode. Then after loading the payload, the transmitter is going to transmit the payload while the receiver is just still waiting. Now, after sending transmitting the payload, the transmitter is going to start waiting to get an acknowledgement to see if the transmission was successful, or it may not get an acknowledgement after so many retries, and then it's going to declare the transmission was a failure. Meanwhile, the receiver is checking its status to see if any data has arrived. After the successful failure, the transmitter will reset, interrupts, and then it shuts down or goes back to the beginning. Meanwhile, the receiver checks the status, and when it knows that the status tells it that data arrived, then it goes, reads the data, then it has to reset the interrupt associated with data, and then it can stop or can go back to listening. So let's look at how we're going to configure the system. So this is the transmit, this is the meaning, this is the receive, and this is the meaning of what we're doing. So for the config, usually the value that we expect for the configuration is 0E for the transmitter and 0F for the receiver. That's important because when we start programming, we have to know what value to expect to see what's going on. So for the config, we have to set up the power up. We need to set up the prim RX to 0, power up to 1, prim RX to 0, which means we're going to be in the transmit mode. We're going to have a CRC, and the CRC are going to be 2 bytes. That's the configuration. Now on the receiving, it's going to be very similar. We have the power up 1. Now the prim RX is going to be 1, which means we're going to be on the receive. We're going to be in the receive mode. That means we're listening for something. CRC is going to be 1, and we're going to see a CRC of 2 bytes. So you have to make sure that the transmitter is set up to transmit mode and the receiver to receive mode, or things are not going to work. Now, when it comes to the acknowledgement, the EN_AA is going to be 01, which means that the acknowledgement has been enabled in pipe 0. We have 0 through 5 pipes, and we're going to be working with pipe 0 on my example, so that's why I auto-acknowledge enable the pipe 0. So that's similar in both the receiving and transmitter. Now, here it talks about the acknowledgement on pipe 0, and this is we are enabling pipe 0. So enable pipe 0, we say, hey, also on pipe 0, we are going to acknowledge to that pipe. Then we have the setting up the address. In both cases, we're going to use a 5-byte address. Next, on the transmitter, when we send the data, we expect to get an acknowledgement. Now, if we don't get an acknowledgement, then the question is how many times should we retry, and how much should we wait between replies? So if we haven't gotten so what we're going to do is we're going to send the message, and we're going to try it 15 times. If we don't get an acknowledgement, we'll continue trying it 15 times with this delay, and after that we'll declare that the transmission was not successful. And to do that, we have the setup retransmission value of 3F. Of course, in the receiving, we don't need that. Now we have the RF channel. So what you do is you set up your channel. The number that you set up here is going to be added to the 2400 megahertz. Now the important thing about this is you want to make sure that you have a channel which is far away from the other channels. For example, the Wi-Fi. So this 76 gives me far away from the Wi-Fi. Otherwise, when you transmit, you're going to be you could be interfered by any Wi-Fi communication. That's the channel. Then we have the RF setup. So we can communicate with 1 megabyte, 2 megabytes. The slower we go, the our better chances of being successful. So we're going to use a 1 megabytes per second, and that means that we have to use an RF setup of 0.6 on both. Next, we have the transmit address. This is the transmit address, and we define that it's going to be the 5-byte address, 1, 2, 3, 4, 5. That's a transmit, and of course, nothing on the receive. Now, on the other hand, on the receive, we have to set up the address of pipe 0 on the receive side. So we have RX address, use to acknowledge return pipe. So this is the DAAD. So this is the receive address. So must match the transmit address. Next, we have the payload size. The payload size in this case is going to be 1. I'm just going to keep it really simple. So I don't want any complications here because otherwise it gets too difficult to understand. Then finally, we have to clear all the IRQs after each transmission, and the value is going to be 0x70. And then last thing, we have to make sure that we have to chip enable after the configuration, and we have to set that pin set for greater than 10 microseconds. So that gives you the idea of how to configure. So let's get a little bit, let's see how we actually are going to do this. So what I have here is just for the transmission, and this is the code that is going to accomplish that. And this is the default values at power up. So first, the configuration. So I have the configuration here. It's in the word config. And then I'm going to OR the what I want it to be changed. So we have the power up, 1 CRC enabled, CRC 2-byte enabled. Now I have to set up this to transmit, which means that I have to set up the PRM underscore RX to 0. And I don't have it here. And the reason I don't is because the bit 0 PRM, that's the default value. I get the config address and the values how I want it to be modified. So set up actually. Next, the auto acknowledge. Here I have it en underscore AA to 1. Next, I enable the data pipe. Then set up to a 5-byte address. Set up the retries. Next, RF channel 76. That's right here. So I say RF channel, and then I put the value that I want it to be at to the 2076. Next, we have the RF setup right here, 06, RF setup 0. We have the transmit address. So how I do that is first I create the array, which is the buffer with 5 elements, 1, 2, 3, 4, 5. I actually have 6 elements here. But so what I do is I write buffers. So what it's going to do is going to take this address, and then it's going to write the address, and there are 5 elements of the address I'm going to write. So that's going to be 0, 1, 2, 3, and 4. So everything is going to work okay because I always put the lengths required. 9, and next we have use the return pipe for acknowledgement. they write uh, to pipe 0. Usually you would put the number when you're going to actually do the writing, but in this case we have just one element, we're sending one byte at a time, so I just put it there for simplicity. Then I have to clear all. So before I get out of the init, I want to make sure that all my registers have been reset, so I know that that they are going to trigger. So here I have the status, and then I use this mask rx ts. So make sure that we have the receiving transmitter and max transmission have been set in the status register. And then finally, what I do is I just set the CE pin also. That's what we do. So now let's look at how we're going to initialize the receiver. So again, the receiver is going to be power up. Now the prim RX, I have to do that here because the default, like I noted, is 0, and I need to set it up to 1 for receiver. We enable the CRC and then the 2-byte CRC. Next, we have the auto acknowledge. And I'll just, instead of pointing back and forth, I'll just let you see it. Number 3, we have the RX, which means we're going to use pipe 0. Next, we're going to set up 03, which means we're going to use a 5-byte address. Then again, we have to use the same channel as before, so the channel is going to be 76, and the setup is going to be 6, which is 1 megabyte transmission. Then we have our 5 address, write address, and I'm sorry, we write to register, and this is the receive address. So the receive address, again, we set it up to be same as what we had on the transmitter. Next, we have the number 8, which is we're going to be transmitting. We expect to get one message, and then number 9, what we do is we just reset all our registers. And finally, we deselect the chip enable. Now let's look at the how we're going to transmit data. So we're going to go chip enable high, transmit the data, and then we'll go to low. So we configure. So we went through configuration. So I'm trying to follow what were the mode. So now let's go to the transmit. So we initialize everything. So now we're ready for the transmission. How we do that? So here we have the data that we want to transmit. Now, so we flash the transmit, make sure there's no data on the transmit. Then we select the radio, and we send the command, hey, we want to load the data. And then we said, hey, this is the data we want to load. And then we wait 10 milliseconds, and then we deselect the radio. By doing this, what we've accomplished is that the data will be transmitted, and this is the data is going to be. So this first section, what we do is we are going to transmit the data. But once we transmitted the data, now we have to get the acknowledgement. So the next thing we have to do is we need to go and check for the acknowledgement. So after sending the data, we wait 20 microseconds, and then we go again and select the radio, and then we get the status from the radio, and we ask the following: based on the status, was it a successful transmission? Which means we send the data and we get an acknowledgement. If it's true, then I'm sending to the laptop a message saying, hey, we had a successful transmission. DXDS sent OK. Now, if this is not true, then I'm going to ask, hey, did we send the max number of transmission? So that would be 15 retransmission. And if the answer is yeah, we sent 15 retransmission and we did not get any acknowledgement, then I'm going to declare this particular transmission not successful, so it failed. Now, after doing that, what I need to do is I need to reset all the register, all the interrupts. So we're ready to do something else, send another message, for example, or complete our or just stop and do error message or whatever we need to do. So let me recap. So we send the message, then we waited to see whether we got the acknowledgement, which case was successful. If we didn't, then hey, did we resend it 15 times? The answer was yes, then we can declare that we had a failure. So now we transmitted something. So we initialize both receiver transmitter. I showed you how we're going to transmit. Now let's look at the receiver. What is it the receiver doing at the same time? So the receiver, what it does is we have a while loop in this case. We can do it by interrupts also. So we have a while loop where we're getting the status. So we get a status. And every time we get a status, we ask, hey, is there data? Did any data arrived? And that would be the mask RX register. So if the answer is yeah, data arrived, then what we're going to have to do is we need to go and get the data. So we're going to do, and we're going to place it in this parameter RX. So we say we're going to do NRF receive byte. And that's the result of that is going to return the byte that we received. And then we are going to display it on the laptop, wait 100 milliseconds, and then do that same thing again. So let's see how this works. What is the NRF receive byte does? So when we call it, what it's going to do is going to select the radio, then it's going to send to the radio the message RX payload. That means, hey, give me the payload that you receive, and I know we receive it because I checked the status. So RX payload. And then after sending the command, then I'm going to send a dummy SPI to accomplish the transfer with the NOAP, which is the hex FF, and put it into the val value. Then deselect the radio. Then very important, I need to reset my my interrupt, because this interrupt is the one that's going to set up the status. And if it's not reset, the status will never get set. So I need to reset my my interrupt, and then I'm going to return the value. That's what I'm doing here. That's what I'm. Now I have another option to be able to do use interrupts. So in this case, I would use the interrupt. So the interrupt service routine is going to be triggered if there is data has arrived. Once I get into the interrupt, I'm just going to check the status one more time, and I do that just to make sure that I'm here for the right purpose, because some noise or something somehow I ended up on the interrupt service routine. So I just double check this, and then Then I ask, hey, if the status states that, yeah, in reality I got data, then go get the data, which is going to be similar to what we did. The NRF receive byte, and then I'm going to display it. So that would be right here. So now with this, you get an idea what's going on for the transmitter and the receiver. So we initialize. In one case, I showed you how the transmitter is going to transmit stuff, and the receive is waiting. Now let's talk about the status and configuration. That's one of the most important things here when it comes to this radio, because let's look at this stuff. So it is essential to have access to the status and configuration register. When working with transmitter and receiver, if the expected message are not being exchanged, you need a way to diagnose the problem. So you have a receiver and transmitter, you set everything up, you push the button, nothing happens. So now where do you go? And that's what they so where do you go? You go and check out the configuration and the status register. So by reviewing the status and config register, you can quickly determine the source of the issue. Well, not quickly, but you can determine eventually the source. So first is you check config first to ensure that the device is in the correct mode, transmit, receive, and power up. So if you have a receiver, make sure it's in the receiver mode and power up. Check status to see recent activities and errors. Compare addresses, channels, and data rate to ensure both sides match. So you do in both sides and make sure they both are going to match. Then you flash the FIFO. If stuck, then retry the transmission. So basically, you see the status and configuration and say, okay, it seems got configured as I had expected, or maybe something went wrong. Now, this is the code that we're going to use to do this. So we're going to have something called the dump register. So what we do is we get the status, and for that I created an NRF24 get status, and then we're going to get the configuration. The configuration is just by using the read register 00. That's all I have to do. So, and then once I get the status and the config, then I print the status and I print the configuration. Now by printing, I'm sending it to the laptop through the UART and seeing what are the status and what are the configuration, and that's what I do. So now to get the status, you select the radio and then you send the NOAP. Every time you send the NOAP to the radio, it's going to reply with the status, and then you deselect the radio and then you're done. So now let's get deep into this, how we're going to accomplish. The NRF24 dump register is a routine that it will display the laptop, the status and configuration register. The idea is that I'm going to, as soon as the program starts, I'm going to use this routine so I'll know in real time the configuration and status at the start of the program. And later on, if I run into any issues, then I can again call this routine and find out what was the status at the point where something went wrong. And it's going to be what I'm going to use to troubleshoot my system, as I explained. So the way this works is the dump routine, the first thing it does, it gets the status by calling the NRF_get status, and then and it stores it in the status, and then it does gets the configuration by calling the NRF24 read register with a 00, which is the config value. Next,
after getting the status, the configuration, then the next thing it does is calls out the print status, which is going to display all the information on the laptop, and then after that it calls the print config, which is going to be the same. So let's look at the NRF print status. So the S value is the status that we got. So the first thing we do is we send the status, we say status register value, and we send the status to the laptop. Now, the first question is the bit 6 of the status a 1. If it's true, that means that the new packet in the receive FIFO is ready to be read. Now, if the 1 is in the bit 5, then we know that the packet was transmitted successfully. Now, if bit 4 is a 1, then we know the max transmit has been reached and we did not get an acknowledgement, which means that the transmit failed. Now, we're going to be looking at bit 5, bit 012 to find out what is the status of the pipe. If the pipe is less or equal to 5, then we know that data available in the pipe, there is data to be gotten. If the pipe value is 7, that means that the receive FIFO is empty, so we haven't gotten any data. If the pipe is on bit 1, on bit 0 is 1, that means that the FIFO is full. Now let's look at the print status. Now, as I was calling this statement here, I have the parse string, which is what's going to be printed out on the laptop. And when we go into the sample program, you'll see exactly what that looks like. So now let's look at what gets printed out on the config. If we have a bit 1 for bit 7, then we can say that the RxDR interrupt is enabled. So we have here, and if it's true, goes up here. If it's false, it comes here. If it's 0, so if it's a 1, then I say, hey, the RxDR interrupt is enabled. That means that we can receive data. Otherwise, if it's disabled, that means that we cannot receive data and we have to enable. So in that way, we could tell that, hey, we're not getting any data, but then we look at the config and it says that the Rx interrupt is disabled, so we have to enable it. Now, if bit 6 is true, then we know that the transmit interrupt is enabled. Otherwise, the transmit interrupt is disabled. So we're transmitting. We have to make sure that this is enabled. Now, this is the max RT. So this means that the max RT also has to be interrupted. Has to be enabled interrupt, I should say. Because this means that the max numbers has been reached or not, or is enabled for us to detect it, I should really say. Now here we have the CRC. Either the CRC is disabled or enabled. So if, for example, one of the program is not getting the CRC, and then I look at the configuration, it says that it's disabled, that the CRC is disabled, then obviously that's the issue, so I have to go in and enable it. Now the next one is CRCO, which means the CRC can be a 1 byte or 2 byte CRC, and we have to make sure that the transmitter and receiver match. Next we have the power up, and we have to make sure that the power is up If we have no transmission, we can look at this and we can see that the power is down. Well, that's the issue. And then we have to look at the PRIM read, which has to be in the correct mode, receive mode or transmit mode. So basically, if we are the transmitter, when we look at the PRIM underscore RX, it better be on the transmit mode, and if we're receiving this, better be on the receive mode. So basically what it amounts to is I have my receiver transmitter, nothing is happening. So first thing I go and I go and look at my status and look at my config. In my config, I'm going to make sure that everything is configured the way it's supposed to, which has to match the receiver. I mean, I should actually say the receiver and the transmitter better match where they're supposed to match, so we have the transmission. So I would be looking for mismatches on the config, and then on the status, I would look at see what happened. Did we the packet was transmitted successfully? So for example, if I'm looking at the receiver and I'm not getting anything, so then I come back to the transmitter and look at the status. It says packet transmitted successfully. That means that the transmitter sent the packet successfully, the receiver didn't get it. So then I would look at the config file and say, okay, is there anything that there is a mismatch here? And if everything adds up correctly, there is no mismatch, then my so we have the receiver transmitter has been set up a transmitter, and there is no mismatch. Then I will start looking at outside, is there any interference that is creating this issue? But the first thing I have to do, I have to make sure that everything adds up here. So let's continue with our presentation.
Okay, so let's go to the first sample program. So what I have here is the configuration of the transmitter and receiver. They're exactly the same, and that's what I showed you before. The only item that I just noticed is that the MOSI has to be hooked up directly. I probably didn't notice that when I did the drawing. The next thing I have is that the first sample program deals with the receiver, but you need to know what you're going to be transmitted, what's being transmitted, so you can understand the data. So the transmitter is going to send sequentially 3 messages. One is going to be hex A, hex B, and hex C, A, B, C. Now we don't transmit the same message because we want to see what messages were dropping. So we don't get A, B, C. We know that something got, if we get like an A and a C, well, the B got dropped. Then the transmitter waits 100 milliseconds between messages. And when it gets to the OC, it just sends everything over and over. So let's see the statement for sample program 1. Listen to incoming message with a fixed length of 1 byte. Use polling to monitor the radio for new data. Send the receiver message to the laptop through the UART display. Use polling opposed to use interrupts. So let's look at the program, and this is where we put everything that I talked about. Put it together. This is where everything comes together. So I'll first give you an overall view of the program, and then we can come back and get into the details. From the header, we have here how we set up the enable and disable the chip enable, chip select, and the first routine here initializes the SPI, initialize ports. We have a routine to do the SPI transfer. Now these are the specific NRF routine to write into a register, to write into a buffer. Then we have a routine to get the status, another routine to flash the receiver, a routine to initialize the receiver, a routine that is going to be used to get a byte once we know something has arrived. Then we have a routine to read a register, and here we have the main routine that it does whatever it needs. It actually initializes whatever it needs to be initialized and goes through a loop where we're going to be waiting for data to arrive. So let's get into the details. So the SPI init, that's something we've done in the past. There's nothing new here. Next we have the initialized ports. Again, that's nothing new here. SPI transfer. So these first three are what we always use to communicate through the SPI. Now the next one, which is the NRF24 write register. As an input we get the register where we want to write and then the value. So we have just the we use the SPI transfer, and we use the write to register, and we OR it to the register we want to write into, and then that's the first statement. In the next statement, what we do is we just send the value through the SPI transfer, and of course before we do anything we chip select low to enable the transfer, and then high to deselect, I should say, the radio. The output from here is the status of the SPI transfer. Now next we have the SPI write buffers. The input for this one is the register, followed by the buffer and the length of the buffer, how many items are in that buffer. So what we do is we just basically send the SPI the register where we want to with the command that data follows. Next we send the data from the buffer. So we just get one item at a time, and we do the SPI transfer. And of course we chip select low and chip select high to select and deselect the radio. Next we have the get status. The get status is kind of an interesting one. Basically what you need to do is just send a knob, which means a 0xFF or a hex FF. If you send that, the radio will always answer with the current status. Next we have the flash the receiver, and that's we use the command to we transfer the command that tells the radio it has to flash the receiver. Next we have the initialize the receiver. So I've gone through this already, so I'll just go really quick. So we have the power up. This is set to receiver. So power up set to receiver. Enable the CRC, and we're going to do 2-byte CRC. Then we enable the auto acknowledge. Next we enable the pipe 0 and 5 bytes address. Here we send the RF channel, what's going to be the frequency, followed by we're going to send 1 megabyte. Next we have to send the address, our address. So this is our the receiver address, and then it places into this ADDR, and then it uses the write buffer. So in the write buffer, like I noted, we have the address where we're going to put the information. the actual address, and then the length of the address. Next we have, in this case, we're going to receive 1 byte. So we just say write to register how many bytes we're going to receive, and it's going to be 1. Now, after all that, what we do is we flash the receiver. Then this is housekeeping. Flash the receiver, and then we're going to make sure that all the interrupt flags are set, enabled to 1 or 0 as it may be. Then we wait for 5 milliseconds, and then we deselect the chip by going C high. Next, we have the receive byte. So what we do is we select select the radio. That means going the chip select to low. Then we send the command to the radio that says we want to read the payload, and follow by the NOAP, which is 0xFF. And when we send that, the radio is going to send the actual value that was on that it received. And once we get that value, what we do is we deselect the radio, so chips enable high. And then last thing here, what we're going to do is the housekeeping. We're going to make sure that our registers have been reset, so we can use them again. Because once you get data, once this is triggered, you have to reset it to make sure it senses the next data, and then we return the value. Now here we have our read register. So what we do is we send the value of the register we want to read. So we select the radio, then we do an SPI transfer, which we're going to send the R register, and we're going to OR it with the register number. Next, we send our dummy SPI message and deselect the radio, and finally return the value. So we finally got to the main program. So in the main program, we're going to initialize the UART, which is we're going to use to be able to see the data. We're going to initialize the port, and then we're going to make sure that the chip enable is low. That's just just in case. Then we start sending our message to the laptop through the UART. So we say, hey, new line, and the first message is going to be hello world. Then after we send our first message, then we're going to initialize our SPI, initialize our receiver, and then I'm going to send the message that says, hey, the NRF24 receiver has been initialized, followed by the dump register. So that's going to give me all the current status and configuration of my radio. Don't forget, this is a lifesaver. So when you get to that point, you're going to know whether or not you've done the thing correctly, the configuration and the status. Then we have a new line. So here we start our infinite loop. So the first thing I do is I get the status. Now they get using the NRF24 get status. So what I want to do is I want to get the status that states that new data has arrived. So I do an if statement of my status and mask receive data. Then if this is true, that means we had received some data, and we go and get that data. So we know we received that data here, but now we have to get the data. So the RX, so we do the NRF 24 underscore receiver byte. So we get the data, and after getting the data, I'm going to display it on the laptop, wait 100 milliseconds, and then do the while again. Now, one of the things I do here, once I get into my while loop, I'm trying to use the minimum amount of communication through the UART with the laptop, because all those things, they create interference, and that could pretty much be the reason your messages don't arrive, because of the interference created by your communication to your serial. So you need to keep that to the bare minimum. So that's why at this point I get my dump register here, but once I get here, I keep as quiet as possible. So let's go and look at the actual results. So here we have our hello world. The item got initialized, and here is status register. This is a E, which means the receive FIFO is empty. That's what I would expect. Configuration is the mask, RX, TX, and MAX. They are all enabled. CRC is enabled. CRC 2 bytes. Power up, and then the device is in mode receive. Now this is what we're getting here is the input from the transmitter. So the input was A, B, C, D, E, F. Now you can see here, let's look at the first one. We have CD, so A, B was dropped, CD, and EF was dropped. So we have A, B, EF, that means we dropped the A, B. So as we go here, we have, I'll just read them so you can kind of get an idea how many are being dropped. A, B, EF, 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 CD, AB, AB, CD, CD, EF, EF, CD, EF. So right now, let's see, CD, EF, and at this point, I finally got a complete set. AB, oh, I'm sorry, I didn't. AB, EF, CD. Here's where I got my first completed. A, B, C, D, E, F. So now the up here I get more information, but I just chopped them off so I could increase the size so you could see it better. So I have here A, B, C, D, A, B, E, F. So as you can see, we've gotten some complete, but a lot of incompletes. So this gives you an idea of everything is correct, but now we're going to have to tweak the installation so we're not dropping so many messages. But I don't know that we're dropping a lot. Maybe that's expected, and maybe when I look at this data, I'll decide, well, what I need to do, I need to send the messages twice or 3 times each of them, and then so that's what you have. And the good thing about this point is I know what I have, and now I know that I'm communicating. If you did not have all this information, you would be just pushing a button, nothing happening, especially if you would need the 3 consecutive messages. So I know that my configuration is correct. I have it right there. I know my status is correct. And then from here, I know what data I sent. So it's a good thing that if you send 3 messages, A, B, C, D, E, F, because then you're going to get a very good idea of how many messages are you dropping, and either you're going to improve your installation, have you hooked up to get rid of the interference that you're getting, or you're going to have to send the message twice. But I mean, you can figure out what to do to make this work. So let me show you here, A, B, C, D, E, F. So we got here another one. So now the other interesting thing is going to be that once we see the transmitter, we're going to see how many of these messages got actually acknowledged, because we're going to be acknowledging all these things. So we can see how many messages got here and how many got acknowledged. And the thing that to realize from this data is that if for some reason the transmitter doesn't send till it gets an acknowledge and keeps sending, that could be a very long day for you. But so we have the radio working, and now to get it to work in a something that you can use it to do some special project, then you would need to figure out where do I take this from. So I hope you got a good idea on this first example. Now let's see if I want to another item that also we have to realize, that the fact that I'm sending this what I'm receiving to the laptop, well, that's also creating interference. So it doesn't have to do anything with the whether or not you have the throughput. It has to be with all this data going through the bus creates a lot of interference. So with that, we can go to continue our presentation to sample program number 2. Okay, so what we did here is we got, this is the, what I showed you was the receiver program and the output from the receiver. Now the basically what that's telling us is that we have communication between the receiver and the transmitter, and then this also shows you how good is the communication. It shows you how many messages the receiver got. And also for each of these messages there was an acknowledgement sent. So then we're going to, later on when we look at sample program 3, we're going to see how many of these things actually got acknowledged, meaning that we got the message, but the acknowledgement did not get to the transmitter. So let's look at sample program 2. Okay, so again, the transmitter, like I noted before, is going to be transmitting three bytes A, B, C, and it's going to be every 100 milliseconds. So in this sample program 2, we're going to do the following. Listen for incoming message with a fixed length of 1 byte. Use the IRQ pin and external interrupt instead of polling. So we're going to actually use the IRQ, which is the PD2 interrupt 0. Next, we're going to send the received byte over the UART to the laptop. So we're going to use interrupts, and when we get a message, we're going to send it to the laptop, and then we're going to be able to evaluate, okay, how many messages did we actually get, and later on we're going to look at the acknowledgement, because sometimes we may be getting all the message, but the transmitter may not be getting the acknowledgement because there is a lot of problem with interference at the transmitter. This program is very similar to the one I just talked about or explained. So what I'm going to do is I'm just going to highlight the differences. So I'll just start by naming the routine and whether or not it has changed. So the SPI init exactly the same. Initialize ports, SPI transfer, they are the same, no changes. The NRF write register, write buffer, exactly the same. The routine NRF get status and flash receiver is exactly the same. Now when we get to the initialization is where we have differences. Now the initialization is exactly the same. We're configuring the radio same as before. What's going to change is that we're going to set up the interrupt. We're going to enable interrupt INT0 external interrupt on falling edge. So that's these 2 lines of code. Now this is new to this program. However, we've already looked at this in the past on how to initialize our external interrupts. And so that's the only difference here. And then we have our deselection of our radio. So the only difference here is we enable the INT0 external interrupt. Now the NRF receive byte, read register, read buffer is going to be exactly the same. Now let's look at the main. So in the main, we're going to initialize UART, initialize port, chip enable low, that's all same as before. Write the hello world, SPI init, NRF init RX is going to be the same, except that on the init RX, that's where we're initializing our external interrupt. Then we're going to dump our register information. And the other thing that is different here is that we enable our global interrupts. So now, every time some data arrives, we are going to jump into the interrupt service routine INT0 vector. And don't forget, the whole idea is that we don't want this polling loop to be going on, because that creates some interference. So we'll see whether or not that really helped or didn't help our cause. So in the interrupt service routine, first thing we do is we disable the interrupt, because we don't want to be interrupted while we're in the interrupt service routine. Next thing is we're going to go and get the status. Now, if we're in this area, we can assume that something has arrived, but let's make sure that is the data we are expecting and not something else or noise or who knows what, but we're going to check it anyway. So we check the status, and then we say if a status is with the mask is on and it's true, that means that the data really arrived. Then we're going to go ahead and get the data, which is the receive byte. So we go and call out the receive byte, NRF24_ receive byte, and then we put it into the receive variable, and then we're going to send it to the laptop so we can see what arrived. And after that, then we enable the interrupt, and then we get out of the interrupt service routine, and then as soon as another piece of data shows up, we'll go back into the interrupt service routine. So let's go ahead and look at the output. Hello world, and I say hello world with interrupts to not show that this is the one on the interrupts, and this is the data arriving. So the status register says as before, the RX5 is empty. I had expected the hex E to get we're okay. Then on the configuration register, we have the interrupt for RX, TX, and MAX. They've all been enabled, so they'll trigger if something happens. We have a CRC has been enabled. We have a 2-byte CRC. The device is powered up and it's configured to receive data. So let's look at what we got. So we have something similar, and I haven't done the analysis to see whether we got more or less. That's something we would maybe want to do. So in any case, using interrupts is a more elegant solution, if nothing else. So we have ABEF, ABEF here, ABCD, ABCD, ABCD. So I don't see any completes yet. ABCD, ABEF, ABCDEF. So we got here a complete message, ABCDEF. And here we have ABCD, ABCD. So I think you get the picture that we are dropping messages, and we tried using polling, we tried interrupts, but still we're dropping some message, and that may be okay. I mean, so because the message are coming up every 100 milliseconds, we get a message. That's a lot of message. So we're dropping, so we may be okay. If we want to turn on an LED, we may want to turn it on 4 times, and we'll eventually get it. And we could turn it off if somebody pushes the button. You can send it 4 times every 100 milliseconds. It's going to be more than adequate. But still, the idea here is to understand that we're transmitting, and when folks say that this radio is great, but you have to be careful with interference and short cables and this, that, and the other. Well, here you are seeing why everybody talks like that and talks about small cables and trying to get rid of the noise. And so here you see the reason. But it's important that you get to this point where you actually have a receiver getting data and a transmitter sending data, and you're going back and forth. But the starting point is going to have to be with your status register and config register. If you get nothing, then you go back to your program and you're going to put a whole bunch of dump data. So every time it goes through the loop, you're seeing whether or not there was anything on the buffer or what happened. So this gives you a fighting chance getting the start register and the config register. So let's continue with our presentation and look at the sample program 3, which is going to be the transmitter. Okay, so let's look at the next sample program. So we got here to the transmitter. So transmit 3 bytes sequentially, hex A, hex B, hex C. After each transmission, wait 100 milliseconds. After sending the last byte, which would be the hex C, restart from hex A again. Send the status over the UART to the laptop for display. So basically, the idea here is once you send, see where you got the acknowledgement and or whether or not you got the acknowledgement. And this is where we're going to find out or realize that the acknowledgement and the receiving data may not match, meaning that you could be, the receiver could be getting all the data, but the acknowledgement is not getting back because the transmitter, there is a problem with the transmitter interference. So the actual acknowledgement is having problem with the interference issue, which is the communication between the message that go between the starts at the receiver and goes to the transmitter. So let's look at the code. So I'll start by giving you a overall view of the program, and then we will come back and get into some of the details. So as before, we have the chip enable and chip select as part of the define. Then we have our SPI initialization, SPI data transfer. Next, we have the actual NRF write register, write buffer. We get the status. We can flash the transmit. We can flash the receive. We have our routine that's going to initialize, is going to configure our radio. Then we can read register. Then we have a routine that is going to send a byte, and then our main routine.
So let's get into some of the details. Now the SPI init, SPI transfer, we've already looked at that many times, so we don't need to spend any time on that. The write to register is same as what we've seen before. There is no change, and basically it's your write register parameter, and you OR it with the actual register where you want to send the data, and after that where you want to write your data, and after that you send the data that you want to write. Now for the buffer, you send the register where you want to write the information, the actual buffer, and how many elements you have on the buffer. So as before, you just send the command, hey, I want to write into the buffer, and this is the data. Next, you have the get status. As before, is you basically send the NOAP. The flash transmit and flash receive, you just send the flash underscore RX or flash underscore TX commands. Now let's look at the initialization. So what we do is we have a command to do the auto acknowledge. Then we have a command that's going to tell us how many times we're going to retries, and the the delay between retries, and basically what it amounts to is every time we send a message we are waiting for an acknowledge. So this says, hey, if we don't get the acknowledge, then we'll send it 15 times, and we'll have a 1500 micro delay in between. Next we have the we're going to go through pipe 0, followed by the address that we're going to use is going to be 5 bytes. Then we have our frequency. Now it has to match, of course, the receiver. Then we have our, in this case, we decided we want to send 1 megabyte per second. And the choice were between 1 and 2. We went with the lowest because that gives us a better chance of the message actually getting there. So that's the RF setup 06. Next, we fill up our buffer with the address we're interested in, and then we actually load the address, which is write register, and the address of the register we want to go is the transmit address tx underscore ADDR. The information is in the parameter ADDR, and there are 5 elements. 1, 2, 3, 4, 5. Next, we want to enable our, let's see, this is the address, yeah. Next, we want to enable our pipe 0. Then we do the housekeeping, which is the flash transmit, and reset all the interrupts. So when something happens, they get triggered, and every time the interrupt gets triggered, we have to reset it. And what we do here, which we've done in the past with the first statement, and it really doesn't matter where you put it, I put it down here. So we're going to configure, it's going to be where at the power up, we're going to enable CRC, the CRC is going to be 2 bytes, and then the PRM underscore RX that I have to set it for receiving, it has to be equal to 0, but I did not set up to 0 here because the default is 0. Next we have a 5 millisecond delay, and then we deselect the radio. So the configuration is very similar to the receive, except that we have the transmit, and we have the address where we're going to transmit, and we have the number of retries and the wait between retries. Next we have the read register. So what we do is we send the register we want to read,
and then we send our SPI no up. So first we actually send our register and follow with the ORT with the register we want to read, and then we do our no up to get the value. So now let's look at this, which is the send data. So first thing we do is we flash the transmit, then we chip select, then we send the command that says TX payload. Basically, I want to transmit data, TX underscore payload. Next, we send the actual data. We wait 10 milliseconds and we deselect the chip, and we do the chip select, send it to high, which is we're not going to communicate with that chip anymore. Next, what we do is we're going to start another communication. So what we do is we say, okay, let's select the radio again, wait 5 milliseconds, and then we're going to get the status. So what we're going to do from this point down is after sending the data, I'm going to wait for the acknowledgement. So that's what I'm starting to do here. So I select my chip again, and then I say, hey, let me get the status. And the status is going to be, did I successfully transmitted the data? And was it successful in the sense that I got the acknowledgement? So this is what I'm checking here. And if that's true, then I'm going to say the transmission sent okay. And else, I'm going to mask the see if I went through max number of retries. So if I don't get the success acknowledgement, then I have to wait until I have sent all the retries. So in this case, it's going to be like I have here 15 retries at 1500 milliseconds. So after 15, I get to this point, and then here I have to state that the transmission was not successful. Now, I did not put that here because we have so many unsuccessful transmission that if I do that, all we're going to get is a whole bunch of message with a successful transmission and not be able to actually figure out how many successful we had. So I left this blank, and you see when I'll show you the output, you're going to understand why I did that. So at this point, what I need to do is I need to clear all the flags, so I'm ready to start again, to listen, to see if to send another message and to wait for the acknowledgement. So let's look at the main program. So let me repeat this just to make sure. So we sent the message, we wait for the acknowledgement. Hey, were we successful? No. Then we keep waiting to make sure we've done all the retries that we're supposed to, and at that point, then we declare failure of that message. And then we reset all the interrupts, so we're ready to send another message. So let's look at the main routine. So we initialize the UART, initialize the set the chip enable to low. Then we initialize our SPI. We initialize our transmit. Then we send our transmit. It has been initialized message to the laptop. Next, we dump our register, the configuration status register. That's the lifesaver. That's what we're going to look and see. Okay, are we okay? Configure and see. Try to figure out why is it that we did not get a successful transmission, or we get the successful transmission. Okay, so once we get to the while, what we're going to do is the following. We're going to send the message AB, hex AB. We're going to wait
100 milliseconds, we're going to send CD. Wait 100 milliseconds, we're going to send EF. Wait 100 milliseconds and do it again. So we'll do that over and over and over, and then we'll see how many successful we got from the acknowledgement. So let's look at the output. Okay, so here we have the initialization was successful, and the status is E. That means that's what we expected. FIFO is empty, so we have the enable, the 3 interrupts, CRC enabled, 2 byte CRC, power is up, and the transmit code, we are in the transmit. So here we can see how we got the sent OK. So the let me run this again. Sorry. Okay, I think we're okay again. And then we wait to get the send OK. Now, what I wanted to show you is that the transmit send OK, they don't match the what we were receiving. We were receiving messages A, B, C, D, or CD, and so forth. So they were fairly quick. Here, the acknowledgement, it really is very slow, and we don't get as many acknowledgement. So if we are our success, we measure it by the number of acknowledgement that we got, then we would be in big trouble because we're getting very few acknowledgement. However, I know we already looked and we know that we're getting the data. So so the thing that I wanted to show you here is that we're communicating. We are having a problem with the acknowledgement, which probably means is that we're having a lot of interference on the side of the transmitter. So, and that's why we don't get the acknowledgement. So it is important that we look at both sides, the transmitter and the receiver, and then based on, it may be that, well, we're not getting the acknowledgement, but we're getting the data good enough, so we are okay. Or maybe that we go back and says, hey, we need to get an acknowledgement for each of the messages. So it is important that we look at both sides and then decide what's good enough. And we need to realize that the installation on the transmitter as the receiver are have to be analyzed and try to get rid of noise, especially if we are expecting to get the adequate acknowledgement. Or we could decide that, hey, what we're going to do is the receiver is going to become the transmitter and is going to send the acknowledgement, I don't know, 5 times for each message it gets. And so there are different ways you can resolve this. And of course, this is just my installation is just you could say a home installation where I just didn't worry about the length of the cable or the noise around me. So anyhow, with this, I think you have a good idea of both sides of the coin. In one side, getting the messages, and the other one getting the acknowledgement. And both of them, you have to decide what you need to do so they are good enough for your applications. So with this, I think we can go back to our presentation. Okay, so let's continue. So we finally got to the summary. So today I gave you a description of the NRF24L01. We went through the schematic, show you how to hook up the radio to the controller.
Then we went through the data sheet. We showed you how to create a framework so you can put your arms around all those commands. Then we looked at some of the parameters and how to mechanize them. And we went through programs, three programs, I should say. Program 1 and 2 had to do with the receiver, one doing waiting for data using the polling, and the other one using the interrupts. And finally, we went through a sample program 3, which was the summary. So I hope you've enjoyed this presentation, and thank you very much for taking the time to spend with me. I hope to see you in the next presentation.